An engineer sets up a steady state simulation around the bridge deck. Mesh looks good. Boundary conditions are clean. They hit run, walk away for the night, and come back to a residual plot that has been oscillating for 12 hours. They tighten under relaxation. Same result. They refine the mesh. Same result. 3 days later, they realize the truth. The solver is not failing to converge. The flow is unsteady, and the steady state framework cannot represent it. 3 days of compute gone. By the end of this video, you will know when steady state is a powerful shortcut, when it is silently lying to you, and the four-step decision framework that tells you which solver your physics actually needs. Steady state CFD makes one strong assumption. The time derivative of every flow variable is zero. Velocity, pressure, temperature, species concentration, none of them are changing in time. What you see at one instant is what you would see 10 seconds later, or 10 minutes later, or never. The flow has reached an equilibrium, and the solver only has to find that equilibrium. This is the RANS framework. Reynolds average, Navier-Stokes. You decompose the flow into a mean component and a fluctuating component, then time average everything. The fluctuations vanish into turbulence model closure terms. The K epsilon family, K omega, Reynolds stress model. What you solve are the equations for the time averaged mean flow. That is why a steady RANS run is so much cheaper than transient. The expensive part of the physics has been averaged away. Many real engineering problems are genuinely steady. Fully developed flow in a long pipe far from the inlet. The velocity profile does not change with axial position or with time. A commercial aircraft cruising at constant altitude and speed, the conditions are stationary, the flow is attached, and RANS gives drag and lift accurately and cheaply. A heat exchanger operating at its rated load, inlet temperatures are fixed, mass flow is fixed, the temperature field reaches an equilibrium. Steady state does not just work for these, it is the correct framework for these. The physics is in equilibrium, and forcing transient on it just wastes compute time without giving you new information. The skill is not avoiding a steady state. The skill is knowing when it is the right tool and knowing when it is the wrong tool. Now, the other side. There are three categories of physics where steady state is not just slower, it is wrong. First, periodic flows. Flow past a bluff body sheds vortices at a well-defined frequency. Flow over a backward-facing step develops a recirculating bubble that pulsates. These flows have a natural rhythm, and there is no fixed point for the solver to converge to. Second, evolving flows. A buoyancy-driven plume from a heated surface. Contaminant dispersion in a room. Mixing in a stirred reactor. These have a clear before and after, a start state and an end state. The whole point of the simulation is the evolution itself. Third, triggered flows. A valve opening, an inlet velocity ramping up, a pulsating pump. The solver needs to march through the trigger event in time. For all three categories, removing the time derivative does not simplify the problem. It deletes the physics you were trying to predict. There is one number every CFD engineer should know, and it tells you whether your flow is unsteady before you run a single iteration. The Strouhal number. Saint equals F times L divided by U. F is the shedding frequency, L is the characteristic length, and U is the free stream velocity. For flow past a circular cylinder at moderate Reynolds numbers, the Strouhal number is approximately 0.2, one of the most robust constants in fluid mechanics. So if you know your velocity and your cylinder diameter, you can predict the shedding frequency before any simulation runs. Now here is the practical use. If you run steady state on a bluff body and your residuals refuse to flatten, they oscillate with a clear period. Measure that period. If it matches the Strouhal prediction, the solver is telling you in the clearest possible way that the flow is fundamentally unsteady. Stop trying to converge it. Switch to transient. Turbomachinery has a special status in this question because it sits between a steady and transient. There are three classical approaches. Frozen rotor. You lock the rotor blades in one angular position and run a steady state simulation. Cheap, fast, gives reasonable global performance numbers. but it misses every periodic interaction between rotor and stator. Mixing plane. You average the flow circumferentially at the rotor stator interface. Better than frozen rotor, captures more of the time average behavior, still fundamentally steady. Sliding mesh. The rotor domain physically rotates in real time and the simulation marches forward step by step. This is fully transient. It captures the blade passing frequency, the periodic pressure pulse that loads the stator each time a rotor blade sweeps past it. If you want efficiency curves and pressure ratios, frozen rotor or mixing plane is fine. If you want unsteady blade loads for fatigue or aeroacoustic noise or any time resolved phenomenon, you must use sliding mesh. Between pure steady and pure transient, there are two important hybrids. Pseudo-Transient. The solver uses time marching as a numerical trick to converge a steady state solution. The end state is steady, but the path to it uses a time step. This is much more robust for stiff problems, strong buoyancy, large gradients, complex chemistry that pure steady solvers cannot handle. The solution at the end has no physical time meaning. It is just a more stable way of finding the equilibrium. URANS, unsteady RANS. You retain the time derivative. You march in physical time, but you still model all turbulence with a RANS closure. URANS works when the dominant unsteady physics happens at scales much larger than the turbulent fluctuations. Slow boundary condition ramps, large scale shedding, gross sloshing of a free surface. It is far cheaper than Liège and gets you a first cut at unsteady behavior. Know when each one is the right answer. Here is the framework I want you to apply every time you set up a new simulation. Step 1. Physics audit. Ask honestly, are there moving parts? Is there a growing or evolving source? Are your boundary conditions changing in time? Is there a known instability like shedding, separation, or buoyant plume formation? If any answer is yes, you are almost certainly in transient territory. Step 2. Strouhal check. Estimate a natural frequency from your geometry and flow speed. If you can predict one, transient is the right call. Step 3. Run steady state as a diagnostic. Do not throw it away. If your residuals converge cleanly to a flat line, steady is fine. If they oscillate persistently, the solver is telling you the flow has a natural frequency. Listen to it. Step 4. Apply domain rules. Vortex shedding, transient, fatigue analysis on a rotor, transient sliding mesh, aeroacoustics, transient layers, cruise drag, heat exchanger sizing, fully developed pipe flow. Steady is fine. Know your field's conventions before you start. Be honest about cost when you justify a transient run. Transient simulations are typically 10 to 100 times more expensive than equivalent steady state runs. Not 10% more, 10 to 100 times more. The reason is the Courant-Friedrichs-Lewis condition, the CFL stability limit, which ties your time step to your mesh size and flow speed. Finer mesh means a smaller time step, and you may need thousands of time steps to march through a single flow through time. Then there is the solver spectrum. RANS is the cheapest, fully time averaged. URANS is unsteady RANS, retains time but still models all turbulence. DS, detached eddy simulation, blends RANS near walls with LES in the separated regions. LES, large eddy simulation, resolves the large eddies everywhere. DNS, direct numerical simulation, resolves every scale and is prohibitively expensive above moderate Reynolds numbers. Pick the cheapest method that captures the physics you actually need. Here is the rule, and I want you to remember it. If your physics has a natural frequency, a growth process, or a clear start state and end state, you need transient, vortex shedding, plumes, ramps, valve events, sloshing, blade passing physics, aeroacoustics. If your physics is in equilibrium, fully developed flows, cruise conditions, rated heat exchangers, steady state is the right tool. Do not avoid steady state. It is fast, robust, and correct when the physics is stationary. Do not overtrust it either. When the residuals refuse to flatten, the solver is telling you something real. Run the 4-step framework on every new problem and pick the solver your physics actually needs. Thanks for watching CFD Toolbox. If you want more CFD content, hit subscribe and check out my other videos on the channel.